Maybe you saw the other announcement, but we have the seminar nominally now till 1:30. In 1:30 to 2:30, magically, at some point, coffee and donuts will show up as a way of introducing the community to the OATS Center and the IoT for Ag Engineering Research Center, hence that banner and that tablecloth. And then at 2:30, we will be piping in virtually one of the IoT for Ag seminars, which is regarding sensors. So you're welcome to stay for as much of that as you wish. You have already come, you can go as you wish. Others may be coming and going also, but at least get coffee and donuts before you go out the door. So that's so that you're aware of the deal. Also make sure, so you picked a good day to come to the seminar because we'll have a free digital and pen for all of you in attendance. And then I'll wait till the end, but we also have some OATS swag for you to choose. All right, so are you already recording?
Yeah.
Okay, we'll have to edit all of that out. Upcoming seminars that we hope you can join us for. So these are the last two in the spring series, Dr. Song Zhang and Vikram Adve. So we hope that you can join us for those on those dates, April 20th and May 4th. Same bat channel, same bat location, just different date. All right, so to introduce today's speaker, I know you can switch to your slides. I've known Professor Krogmeier now for probably 10 or 12 years on the order of that. So I'm going to give him a good solid introduction here. He has Colorado roots, farm roots. His family did some commercial baling back in the day. He is still active in owning and assisting now with the corn and wheat dryland farming out there. It's under irrigation, part of it. And so that presents some unique challenges. It also offers some good research opportunities that he might allude to in his presentation today. So his first degree in engineering was electrical engineering from the University of Colorado Boulder. He was sort of deviating or trying to decide between electrical and ag engineering and made the wrong choice then, but came back later in life. He's got his MS and PhD in electrical engineering from the University of Illinois at Urbana-Champaign. In 2 words, Professor Krogmeier is all about signal processing. In more words, it's things like statistical signal processing, wireless communication, networking, all aspects of the data pipeline, and with applications, and let me emphasize, applications in agriculture and transportation. He was on the technical staff at AT&T Bell Labs in New Jersey, way back in the day, did a postdoc in France. This is my translation of the place. It's the National Superior Telecommunications Center, or however you say that in French. He joined Purdue in 1990 and has, of course, moved to the ranks of professor since then. He founded the Center for Wireless Systems and Applications, which is, I think, still on the Purdue books, but sort of defunct. That's actually how I met him. In the Center for Wireless Systems and Applications, they were ahead of their time with things like eStadium and other projects. He is very active in IEEE, in the wireless communications and intelligent transportation systems. He does have a courtesy appointment in EBE and spends a good chunk of his time, office time there. He had a vision for the Open Ag Technology and Systems Center, and that's what he will be presenting about today. The OATS Group, which is now a center, spawned several industry collaborations. We have an annual OATS conference. I see he's sporting his name tag from the most recent one still. OATS, the center, has instigated, inspired, or otherwise supported educational initiatives for graduate students and undergrads as well. He teaches or has taught linear circuits, electronic circuit analysis and design, signals and systems, probabilistic methods in electrical and computer engineering, digital communications, advanced digital communications, estimation theory, and also one of the things that pulled us together was the vertically integrated projects in electrical and computer engineering. He was very instrumental in the NSF-funded IoT for Ag Engineering Research Center, led by University of Pennsylvania, partnered with Florida, University of Florida and University of California, Merced, and Jim was on the Blue Ribbon panel that turned the lock on us actually getting that project funded. He has research funding from several ag and tech companies, from NSF, USDA, NIFA, DARPA, NDOT, and probably a lot more than I ever knew about. So he is also now the Associate Dean for Facilities and Operations in our College of Engineering. I hope you learn from and enjoy hearing from my very close friend and colleague, Director of the OATS Center, Professor Jim Krogmeier.
Wow. Thank you, Dennis. That's a nice introduction and I guess true. Mostly, I'm definitely the Associate Dean now, unfortunately. I found out that's quite the job and didn't really quite realize that completely. But here I am today. I've never been as far behind in 3 weeks on a job as I am at the moment. I want to talk a little bit about OATS Center. It's sort of, as Dennis alluded to, it was sort of the death of East Stadium that sort of brought to life the OATS Center, because we were considering shutting it down because it, you know, it sort of had run its course. Technology had caught up, and the Purdue had signed, the Big Ten had signed a new TV contract, which made it very difficult to deliver videos to mobile devices inside the stadium at that point, you know, so it made it sort of illegal. And that then shut us down. I think we were looking for the next cool thing to do. Aaron Alt was a part of East Stadium. He's a farmer from Indiana. I have farm background. I think maybe we called up Bernie or somebody and said, who should we talk to? Connected us with Dennis. We met, and you know, it's been a wonderful collaboration. And it's really the foundation, if you will, of the OATS group, later OATS Center, but really kicked off by a grant from the Foundation for Food and Ag Research. And that was a big and important deal. And we can certainly thank many people at Purdue for that as well, who were there and sort of encouraged us and helped us along. OATS Center was really founded to build a community of researchers that cared about agriculture and data and sensing and open source in order to make these sorts of innovations more usable and translatable to practice. That's what the FAR mission really is, to make things translate things to practice. So that's what started us. We came up with a snazzy little vision or mission statement here, which really just says, we're working in these areas, we innovate, we do research, sensing, control, logistics, data, communications, all of these things we work on, and probably even more than that, but focused a lot on educational outreach, community building, and delivering some of these things for the world to use. So that's the open source part. Not only software, but also hardware projects. And toward the end of the talk here, you'll see some examples of those things. The group of people that have either have been willing to join or listed in this group of pictures, all would be welcome, but you know, we're not twisting anybody's arm, and lots of people got a lot to do, and it's probably is all that we can handle anyway. A few of these I will highlight a little further down here, because I want to talk a little bit about a sample of some of the projects that OATS faculty are working on. Then I want to talk about the ERC. And lastly, I want to talk about this sort of rather interesting new idea that we have to create an instrument that could be located at Purdue ag farms or even at other universities as well, depending on how big it could go, to allow for autonomous sensing and control. And it's really motivated by our journey in the IoT for Ag ERC, trying to find what's the right test bed. What is the test bed for this sort of development? But first, these projects from some of our faculty, and I just sent out a call to people and said, hey, do you want to send me slides? And some of them probably were looking at their email that day and did send them, and others were too busy and probably didn't. So, but anyway, going to that, the first one that I have listed here is from Dennis Buckmaster, who leads a program in the REU called Experiential Learning with Data Tools and Digital Agri-Science. And I'm on this. In the summer, I guess probably just go here. In the summer, we run a 10-week summer camp. It's broken up into some segments that involve teaching people things, teaching them about spreadsheets, teaching them about GIS, teaching them about Python. Python is the part that I handle in this, and R, and trying to integrate that into some projects that the students then carry out over the course of the summer. It's really a combination of lab, classroom, homework, and a project. I think this is the last summer it's scheduled to run, but it's been an enjoyable time. And you can see here, of course, there's been a fair bit of disc golf played. Dennis is a big fan of that, and it's hard to get out of it if you're around when he comes looking. There's a few more slides here. I may not focus on them very long. Dennis made this little talk to send to the USDA, so it has both good and bad in it. It has sort of lessons learned. Do we really care about these lessons learned? Well, we do, but perhaps not in this talk. What I liked was the pictures. So I wanted the pictures at the bottom to show you some of the students that have participated in this, and this made me quite happy. Josh Bailey, who's there at the far right bottom, the fellow leaning over and working at the computer, was an alum of this program and now a graduate student here, has written a proposal that's actually been funded, and his family runs a farm in Michigan, and some of the technologies that we've developed are being deployed there under the auspices of this grant and more. So to me, that's just, a remarkable sort of story about how he could take the REU program, learn these tools, become a graduate student, and write a proposal that gets funded. And you know how hard it is to get a proposal funded. That's pretty impressive and good for him. Very good student too. So really the accomplishments of this whole thing are about these students and about, what they're doing and, how this is helping them. And one of the neat things that Dennis has done is we hold a reunion with these students, try to figure out where they're at a few years later. So bring the whole group together. And it's also been a kind of enjoyable thing. There's, of course, lessons learned. I think I'll split or skip from that. But I believe this picture here at the bottom is perhaps us showing people how to build something up there in the AVE space, is my guess. Okay, moving on. We've got other ones to talk about here. Professor Chatterjee is really kind of she's an ag and bioengineering assistant professor. She's also a professor in ECE by courtesy and works in neural nets and machine learning. And she has a couple of slides here to talk about what she does really in the sort of computer vision and cloud computing space, especially for IoT and sort of edge computing type computing capability. So she's worrying a lot about how you balance that workload between, say, the cloud and the edge, especially when you've got energy constraints and communication constraints between them. And so there's a fair bit of work in how that problem is solved. She actually looks at it as a game theory problem, and she sort of comes up with a scheduling algorithm that chooses between these costs and sets up a little game in order to decide what's the right way to do that. Beyond that, I don't know too much, but it's been award-winning work. She's done very, very well with it and has a career grant, I believe, as well. This one I'm particularly fond of, mostly because it's exactly the OATS Center at work. This is the picture in the upper left. There is Amy Riebman and Jackie Borman. Amy's in ECE, and Amy is an expert in video and video analytics and image processing. At one point, very interested in using video to analyze the movement of humans, their gait in sports medicine and things like this. But also looking for applications and how to be relevant in this world that we live in, and came together with Jackie Borman, who works in dairy and animal science. And these problems are really things about how do you track cows in a barn? How do you create, as they call it, a cattle log, which is the middle row there. They actually can do this with one image taken from the top and a template matching algorithm that picks the important points on a cow and then is able to create an identifier for that cow and find it again when a camera looks at it. She also has done some things in the gait detection. That's at the lower right of the thing, looking for lameness and these sorts of things. And in addition, being able to use her algorithms in a real context, in a real barn, where you're going to be looking through fences and other obstructions. You may have dirty cameras, these sorts of things, but the real practical questions about how this stuff works. Amy has been working on that with Jackie, and they've managed to secure funding to do these kinds of things. And really, they don't need me anymore. I mean, they're doing just wonderfully, and it's exactly what a center of this nature is supposed to do. Amy's also connected with Amanda Deering and has worked on, control of foodborne illnesses and actually systems that help people to do a better job of washing their hand when they're in the food production process. So they have an experiment here where they watch people's hands. They give them some instructions here on the upper right there and show them how to wash their hands, then watch them do it. And the system is able to sort of say which parts are missing. Are they missing certain procedures and this kind of thing automatically in order to create perhaps a system that would remind people. I went over there that day and I remember reading this very, very well. And I did their tests, and it was probably the best hand washing I've done in maybe even through COVID, although I do remember thinking of these lessons learned in the middle of COVID, believe it or not. It's probably why I survived. I think that might be my hand even in that picture. It just looks a lot like me. And I was really trying to do it right. I remember that. John Jin is a professor that works with us also in the OATS Center. Really, I guess I would call him remote sensing, sensor design and system design, and also algorithms for looking at the data. But I would say he's probably a little more focused on the design of the systems and the hardware and the software that do them. You see here greenhouses of various sorts, some work that's going on in the phenotyping facility, and then this gantry that Jin has shepherded being built out there at Acre, kind of in a way sort of the precursor to some of the ideas we've had with the pivot. In addition, he has a device that is marketed that is actually able to sort of create a high signal to noise ratio image of a leaf showing various multispectral bands as it goes there. And he's also working on robotic operation of this scanner, so that it's not just a human being necessarily that has to walk out there and scan every leaf. I mean, that's one of the main takeaways really is there's definitely a need for automation in these things. If you're gonna be out there scanning, you got a leaf scanner, okay, that's great, it's the best leaf scanner in the world, but there's hundreds of thousands of plants in a field. The human effort of scouting, the human effort of going out there and doing that probably makes many of these things unattractive or not useful enough anyway. And so how do you automate that is a big question for Jin. We work a fair bit with Bruce Erickson because one of the things that, of course, our whole focus in translation and open source gives us then a focus at understanding when does technology get adopted. So Bruce does a lot of study on this sort of thing and has been doing it for a number of years. I think it's maybe the longest running survey of adoption of precision agriculture technologies that he works on every year. He's also does a fair number of classes along these lines, and there's an interaction between the OATS Center and one of the major standardization groups in precision ag called Ag Gateway, and he helps us with sort of our outreach to that group as well. Okay. And then Melba, hello, there you are, Melba. Remote sensing, I guess, I'll characterize Melba's work, but she's sitting right here, which is probably a very bad thing to do. But no, I think it's probably good for you to hear what I think. That way you can correct me if I'm wrong. But I see Melba's platforms as being farther away and closer both, maybe a broader set of platforms than, say, Professor John Jin, space-based things, aircraft-based things, and UAV-based things. I see Melba as a pioneer in the algorithms that work with this data and in machine learning and nascent AI attempts to use it. So, you know, I think, and well, I think that may be the slight distinction between them, but I think Melba mostly uses available technologies for sensors and things like that, and her work is primarily in the algorithms that work on that data. So it's a little bit different perhaps than the other. Here's some work that they're doing on remote sensing and coming up with models for yield prediction. Looking really, here's a LiDAR point cloud, which shows the plant canopy growing over time. And there's some measurements that have been made over here. And actually a fair bit of neural network sorts of technologies applied to this. That's one of the, of course, the big hot areas that people want to look at is how can we automate and speed up the analysis of this sort of data, because this data is large and difficult to handle, and certainly not amenable to human operation for the most part. Here's some work that really kind of tries to close the loop here, also using sort of transfer learning. Again, that's one of the big issues in a lot of this sorts of thing is that we can train algorithms, but data sets for training are sort of difficult to come by. And you often want to train something up, say, for one crop and move it to another crop, or for one situation and move it to another. How effectively does transfer learning work in applications like that? And that's probably driven, and we can ask Melba later, but it's probably driven by the fact that training and these sorts of things they're bottlenecks. They're bottlenecks in applying these things. And so therefore transfer learning is extraordinarily useful. Okay, now I'm done with talking about things I don't know. Well, a little bit of things I don't know, but I'll talk a little bit more about the ERC that we're a part of. So the OATS Center and several of the OATS Center members, all of them are in this IoT for Ag ERC. And we were sort of fortunate, I think, that we sort of stumbled into this, perhaps knowing Dave Capillari was key, you know, but he knew the right people to talk to, and it's been a really good thing. And I was really pleased, actually, that some of my old-fashioned farm boy sense about how these things ought to work, you know, was useful when we went to Washington, because the panels sitting there kind of wondered, is this going to ever work? Will this work? What's wrong with it? You know, why should we trust you? You look like a bunch of people from machine learning and nanotechnology. What do you know about farming? You know, so I think I was able to serve a role there that sort of gave some credibility to the idea that this whole thing could possibly work. And we lucked out and we got it. And now, of course, we're stuck with trying to figure out what to do and actually succeed at it, which is another matter in itself. And I think we're having some success, but on the other hand, these are difficult problems, and you know, we need a lot of help. It's a 4-university ERC. It's led by Penn. Purdue sort of handles the great middle part of the country and row crops like corn and soybeans and these sorts of things. Florida and California handle the citrus and fruits and fancier, I guess, crops. There's some differences between them, but you know, they look a lot alike, at least in terms of the crops they're looking at. That's supposed to represent really kind of a fairly large diversity of agriculture across the country that might be interested in these things. The work of the center is broken up into 3 basic areas. I'm calling the thrusts here, but one is sort of agricultural sensor systems and their development, and this sort of is really where the nanotechnology comes in. People are looking at various sensors that could be affixed to leaves or fit in the soil or be made the size of seeds in order to get right down there where the thing that you want to sense is. And then there's the second part in the middle, which is kind of the backbone of it, if you will, the communications that allows you to read off the sensor, maybe the energy system that allows you to power the sensor. Because one of the big things about, you know, an agricultural scenario, especially at scale, is you're just not going to be going out and planting a lot of batteries and not picking them back up. And even the planting of batteries, period, It's not recommended because you'll never pick them all up. So you've got to be able to produce something that you're going to measure these products in the soil, and it needs to be biodegradable. It needs to work, and it needs to probably disappear at the end of the season, because the practical aspects of going out and finding it are pretty much insurmountable. So that's a recognition, really, that these sensors need to be powered or remotely powered from infrastructure that isn't buried. The other aspect of it is sort of the closing of the loop, this thrust 3, which is the response systems. How do you come up with models and analytics and control actions that change something about how you're growing corn or soybeans or fruit or citrus? In the absence of that, it's all kind of empty. And in fact, the ERC, our goal in the ERC is really to close that loop. Here's a few more slides that show you a little bit about the types of sensors people are working on. This is a project that Sherry Kagan, who's the PI of the ERC, is running, and she's building these metamaterial-based sensors that affix to the leaves of plants. Depending upon pH or transpiration or temperature or humidity, the sensor may change a physical property in it and change the way it behaves under some illumination. So that's shown here in that frequency shift that she's seeing. So, she's looking for how does she raise the quality factor of that response so it's easier to see in noise. But there's another major problem that Sherry's not working on, at least not at the moment. That major problem is, how are you going to fix it to the leaves? Clearly, we managed to stick it on one leaf out there at acre, but to make this thing a practical thing, there needs to be engineering that's designed as to how are you going to put them on all the leaves, or not all the leaves, but one every 1,000 leaves automatically without a human being going out and doing that. These are some of the questions that a testbed like acre, like Purdue, ought to be trying to answer. And it's one of the reasons why ag engineers are on the project, because it's kind of an ag engineering discipline to figure out how to do things like that, I think. There are other sensors. This is Troy Olson, who works he's more of an RF person, at least in my category of people. He's building sensors that we can vary, and that some sort of property of the sensor, like say its capacitance, changes in response to moisture. That can be read back out by looking at where is the resonance of some circuit upon excitation. So maybe with an RF interrogator, something reflects back from this tag, and the frequency is determined by that tuned circuit element, a capacitor. Capacitors are things that store charge and create what's called a tuned circuit in electronics. And so you can see the response change as to where it responds well, depending upon the size of that capacitance, which is then related to the soil property or the plant property. Robotics work here at Purdue, wireless charging work that's based at Florida, and then Melba's project here, which is sort of monitoring the flowering of row crops, also are part of IoT for Ag. This is the thing, though, that kind of brought me to where I'm at. It's really just this recognition. And it's actually from listening to the NSF's critiques of our center over time, and even during the review process, that, it's going to be hard to build a test bed across 3 or 4 universities and actually close the loop here. But in effect, this is what we really promised. We said we would do it, that we would be able to build integrated systems that detect and allow us to intervene, and some sort of control action is demonstrated that improves things, either applying more water or applying pesticide or doing something like that. We're certainly not there yet, but we're trying very hard to get there. And so some of what I want to talk about is our efforts to do that. We have 2, and this is really right in OATS group, because it's kind of what OATS group has done all along. We see this as a need in the ERC, and so we're offering ourselves and our efforts and our expertise to do this. Namely, that if we were going to enable this integrated testbed operation and to be able to do it at the scale of fields, not just single plants or greenhouses, we're going to need to standardize the IoT for Ag hardware and software interfaces, because the folks working on new sensors in nanotechnology typically aren't necessarily working on that end-to-end system. or they may not be as good at it as us. So what we need to do is be able to build these kinds of interfaces and standardize them so that they're able to design to them in order to be able to then actually mail us their stuff, and we plant it out at Acre and see how it works. In the longer term, I think we also need to be thinking about what is the instrument that holds this all together? What is the way that ag research on research farms creates data sets that are really available for the world, rather than kind of the hodgepodge way we probably do it now, which is researcher by researcher, depending on what they do and what agreements they've signed with their funder about how they will treat their data. I guess I'm just saying that from the perspective of someone that wants the data, a signal processor, it's pretty hard to come by, actually, for a lot of reasons. In many cases, data is created in the process of doing an experiment that's run out at Acre and run under the auspices of some agency or company that's funding it. And they surely do not wish their data to be released until all the goodies been got out of it, for a variety of reasons, right? So that then means that even if you do release that data 3-4 years later, it's pretty much obsolete at that point when we make it available to the world. So there's sort of that time lag that is a problem. And then also just that usually funding mechanisms don't really, in spite of the fact of writing data management protocols and things like that in there, they don't work all that well. What happens is you zip it all up and you send it to PER, and that's the end of it. It's a place for data to go to die. That's a nasty thing to say. I don't really mean it. We have some of our data there. It's just that getting it out of PER is a big job, and it comes in a big old hard tar ball thing that you got to go through and look through. It does not come findable, interrogatable, searchable, and automatically. And until things come automatically, you just don't use them for the most part. So people don't much use it. And so that's, again, that leads us to sort of the end of my talk here, showing you some of the things we've done here to try to create a hardware interface. And we sort of have two aspects to this hardware-software interface. One is for sensors that produce very low rate measurements. So like a moisture sensor in a field. This does not need to be reporting 10 times a second or anything even higher than that. It does not have a lot of data to send. Those properties don't change very fast. And so they're a network that's good for handling thousands of sensors, but at very, very low duty rate cycles like LoRa. That's the right way to go. And so we've built, we're working on and built a LoRa network that runs at Acre. And we have a mechanism by which, if you have a new sensor, you can interface it to a LoRa module that you can buy. And we're working on that actually right now with people at Penn. So our group is helping some of the nanotechnology people at Penn integrate their technology with a LoRa sensor so that we can send it here to Purdue and read it and demonstrate that this is a feasible thing to do. In addition, we're building out open source based software environments that allow this to work, so that if that group at Penn builds their device, connects it to the internet at Penn, and if we can solve all these internet issues that we seem to have, especially with security, which scares the crap out of me. Not getting hacked, that doesn't scare me that much. I know we're going to get hacked. It's the fact that we may not be able to communicate anymore in order that we don't get hacked. So that's a discussion I think we need to have probably as a university, because if we're going to make data available to the world, there will be people doing bad things, and we need to be able to handle that. But at any rate, the idea here, and it works right now, is that you can design this thing at Penn, you can connect it to the internet, and it automatically brings its data to Purdue. And when they mail it to us at Purdue, we take it out to Acre, and it connects exactly the same way and immediately and autonomously and automatically. So that's pretty cool. Think about it. Now they FedEx their experiment to us. It will fill the same tub of data that it was filling in their lab back at Penn. And they can do it at Florida, and they can do all these things. So that's pretty interesting and pretty cool. And it's really just us putting together the open source pieces that allow this, and the fact that Purdue up till now has been kind of easy going on how you handle networking. They've been willing to let researchers do things not necessarily all locked down. So if that changes, this could make this a lot harder. But it'll make everything a lot harder too. This device that you see here in front of you, this is called a Purdue OATS data station. And it's a LoRaWAN gateway that connects to sensors out in the field. We deploy these out at Acre. We've sent them to Florida. We've sent them to Penn. There's one running at Penn through our network now. And that, again, is the success of this endeavor to actually try to really show how you can put data in both places and have the software systems be seamless and work. For higher rate data, things that are going to run on a tractor, so that's very, very low rate LoRa data. But for stuff that's going to run on a tractor, which I'm calling high rate, but isn't really high rate, but things that are on the CAN bus, so the tractor or machine sensors attached to that sort of megabit per second rates. We have a device that we call IsoBlue, which is telematics. It's an open source telematics device, and it runs a software stack that we call Avena. Avena was named by one of our students. I don't see him. One of our students named it Avena, but Avena is just Spanish for oats, so it's maybe a little redundant. But anyway, it sounds nice. All these sensor packages can use power over Ethernet that we're designing here. It basically works on any sort of fixed machine that has a reasonable amount of power. Running it on a UAV, on a flight package, is another challenge. Probably it's doable, but it's not something we've looked at. We've stayed a little bit in my group anyway. We've stayed a little bit away from UAVs. We have other, there's plenty of folks working on UAVs. They don't really necessarily need me. One of the interesting things about this, though, is it shows a picture of Deere's telematics gateway. And so one of the things that happens, of course, in a center like IoT for Ag is Deere's a member of the center. So you go to Deere and they say, it's all problem solved. Why are you doing this? You can just use our gateway. Well, you can send your data all through our stuff. And if you don't care what we're doing with it, but you don't get to change our gateway. You don't get to put any software on it. You don't get to do anything you want to do unless we want to do it. So the problem with that is it's fine for a product in the world, but it's not so great for a university research project. The thing is, though, if Deere wanted to, they're running Linux on their gateway. We're running Linux on IsoBlue. We've got a system here that could run on theirs, and they could allow our experiment to run next to their experiment and keep the data apart. So it's a model for how Deere could open up more like Android, or let's not say Apple, let's say Android, and allow developers to develop on their platform if they wanted to. And sometimes that's the right role of a university, to show that something like that is doable and to sort of understand perhaps the implications of doing that, at least in our endeavor, and then they can make their own minds up. Coming back to IoT for Ag, we of course need viable platforms to create the things that we're going to be doing out there at the fields and at the farms. We need nice tractors. I think this might be Mitch's tractor. I don't know, probably can't have yet. But we are going to get to use the Pheno rover this summer, which is a kind of nice thing. We're actually going to run a trial where IsoBlue Avena is talking to buried RFID tags. We're going to experimentally design this trial and figure out, what the orientation of the tag and what the depth and what the height above and the speed that we drive over them, how that affects the reading of them. And we'll create the software system that will read those tags and create a swath map in the cab or on your phone so you can see where it read them. And that thing will be demoed, right, Ashwin? That will be demoed this summer in Florida. It'll be running here at Acre, and they'll be seeing it in Florida. So help me. Sorry, Ashwin, I didn't mean to do that to you. But we actually have a number of people that are working on this, but it's an important demonstration, because then these are 900 megahertz remotely powered tags. They're not battery tags. Once we demonstrate that, sensors built by nanotechnology folks can certainly be integrated with that technology. And then the sensor can be read remotely by a sprayer as you travel over the field. And we can understand that because now we've done the systems engineering on the I guess, the farmer side or the OEM side of the equation of how you do that. I'm very happy and excited to be able to use that platform because it's almost perfect for what we need for this year. Okay, I guess I've spent a lot of time. I don't know how long am I supposed to talk, Dennis?
Oh, another 15, 20?
No, it's perfect then almost. So at some point it occurred to me when we're talking about all this autonomous stuff, you know, and UAVs and such, and it's just, I don't mean to diss UAV technology. I think it's a cool thing, and who wouldn't want to fly? You know, I mean, I love to fly, and the idea of being a UAV pilot is like as cool as anything could possibly be, except maybe being a real pilot, you know. But then in a real pilot, if you crash the plane, you're in trouble. But you know, UAV pilots probably not quite so much trouble. So I like it, and I think it's, you know, it honestly is surprising me here and there. You know, there are things that people are doing now with these that are a little more impressive than I thought they could do. You know, I thought that the throughput, the ability to use them over large swaths of land might be problematic, ultimately a problem. But I'm not so sure that that won't be solved. I guess the point I'm making, though, is that there's a lot of development going on in how UAVs work, how you power them, how long they will fly, how you control them, what is autonomous operation for a UAV, because today you really need a pilot. You can't really operate autonomously, or at least you're not legally allowed in most places to operate autonomously. I think you could do it, you're just not allowed to. And the sensor packages that it carries, and the bandwidth off the UAV, if you need to see the data from the UAV in real time, or even to just kind of get it automatically so that you don't have to manually get it off of there. All of that research, which all of those are important problems, they're all commingled, they're all dependent upon each other. And so it would be my contention, or it kind of was my contention, that that complicates the solving of the problem of figuring out how machine learning and AI algorithms can figure out yield or detect pests early or things like that, because it's dependent upon whether I can fly my UAV, how well that research is going, and they're all kind of mixed together. I think often when you mix research together, you have an uncertain platform, an uncertain sensor, an uncertain algorithm. They've got three things that can go wrong, and they probably all will. You know, and so what I'm trying to do with this is find a platform that is already autonomous, is already basically worked out, and that is a center pivot irrigation system. And so that's my idea. I want to build a commercially available irrigation system as a platform for sensing of all kinds and for actuation. I want to sense things going on below the soil as well. That's probably a little harder problem, because if I'm going to do it with tiles, you know, tiles are expensive to build. It's probably the way we want to go in the long run, but in the short run, it may be something that we don't completely do. We sense point sensors, that sort of things, you know, buried there. We read them from the pivot. Pivot we look at here might be something like this Valley 8000. It's their nicest, fanciest machine. Okay, I show it here on acre. Forgive me, I don't know that it will go on acre. So if your favorite field is right there next to it, and you think, oh crap, he's going to be driving across it with his darn circles, we don't know that. You know, this is how you get stuff done. If you tell Mitch you're going to go out there, he's going to want you to not make it a pivot, because he's had experience with pivots and he don't like for experiments. I mean, here I am characterizing your opinion. Well, I don't know where it'll be. I'm hoping it will be at acre, because that's a nice convenient place for it. It could also be that it goes out at Azric. It might make sense to take it to a fields where we're not trying to plot too much under it right now. It might make sense at TPAC. That's all something we have to figure out. But what I want to do here is I want to basically create the largest robotic sensor, as far as I know anyway, in the world, which would be a pivot. They're truly autonomous. They've been autonomous essentially for 50 years. You know, you can move a pivot around. You do not need to be there. It'll go at night. It'll go during the rain. Sometimes they get stuck, but you know, for the most part, they go. And that's quite a remarkable thing, because a lot of these sensors that we're trying to design, in IoT for Ag are optically read. Well, this optically read sensor may have some issues in the high sun or in the shadows in the canopy when you're unable to control the ambient light very well. You might be able to measure it, but maybe not control it. Or perhaps you don't have the, you don't have the band you exactly want, but you can come around at night with a particular lamp and excite a certain range of wavelengths and then see the response of the sensor back. That would be cool. And if you could do that for thousands of plants automatically, that would even be cooler than that. So this all comes down to, how can I get data across this pivot without doing a lot of wireless? Because that's another thing. I love wireless as much as anybody, but wireless in these applications at gigabits per second over long distances sometimes is also problematic. It's still a little bit under development, some of these bands. So my idea here is, let's put fiber along the pivot. Let's be able to put a fiber connection to within a square foot of ground 10, 15 times a day, if we want to. And to be able to have 100 gigabits per second on the backbone of that pivot so that I can share that network with hundreds of researchers. People could be logging in from Penn and run their experiment out there. That's the idea. Interestingly enough, it's been proposed. I've been proposing it for a while now. I proposed it to the NIFA equipment grant program, and they said no. They said it might. They said it might interfere with the UAVs. If it's moving so fast, it might hit one. I think that was what one of the reviewers said. I think he misunderstood something I wrote, which is clear that I didn't do something right. But the other thing I would say is the NIFA equipment grant program is too small for this idea. This is a big idea. It wasn't enough money, so they're probably right. So the things that we imagine being on this, and finally, the National Science Foundation is funding parts of this. So we have a planning grant, and we're working on a design proposal that's due in May to sort of begin to build this out, to experiment and build components of this system that we need to be able to do this. So we're going to need the gantry itself, and I've said already that the gantry is really a solved problem. The gantry, well, it may come back to bite me, but the gantries are reliable and they're well engineered and they're well understood, and they last 25 or 30 years. So that's pretty cool. We're going to need networking along the gantry. We're going to need fiber, and we're going to need something called a fiber optic rotary joint, which is a thing that would allow it to go all the way around. Yeah, we could also wrap the cable. We could have it wrap and then go the other way, or windshield wipe like you do in some places. If your house lives over here and you're in Phillips County, Colorado, you don't want to run over your house, you windshield wipe. But as a research instrument where you want to be able to get to any piece of the field quickly, if you've got some sensing schedule you're trying to meet, you want to be able to go all the way around. It's just going to be a lot better. And so to do that, I'm going to need to be able to rotate that fiber, and I really need to be able to get a lot of bandwidth through it. Pivots today already send electrical power through that same joint. It's that little cap that you see right over the pivot point. That's the rotary joint right now that passes three-phase power to power the motors. Well, as it turns out, there are fiber optic rotary joints. They were developed for MRIs and CT scanners and radars and windmills. That technology is pretty well understood. And in fact, they also integrate that technology with electric. If you think about a windmill, these kinds of things are things that you do. So really what we're trying to build here does not rely upon a fundamental breakthrough in technology. It relies upon design breakthroughs, if you will, in integration, and maybe operations. Operations is something worth talking about as well. How are you going to use this on a research farm? How would it make sense? The idea here is that research packages are provided by the users of the system. And in order to do that, we don't want them to have to harden their equipment. We don't want them to have to worry about the fact that it's going to be 115 degrees in the sun out there in the middle of July. And if you take a thing that you just built in the lab out there and sit it in the sun, it's going to run about 5 minutes and quit, and it's going to overheat. You know that'll happen. It will happen. And so it's a very difficult problem. It's suddenly an engineering step required to get your experiment on there. So our idea here is, given that pivots have a lot of power, is to put climate control cabinets on every tower. And that way you can bring out to that pivot and stick it in a slot in that cabinet, something that actually runs in the lab. And it does not have to be hardened or over designed. The other thing that happens typically when you're able to harden these things in order to make them run in heat or in terrible conditions is that the performance you can get is lower. I really want to get the highest performance that networking computing will allow out there in that edge computing, so that some of the problems of computing and networking that are bottlenecks for research for agronomy and sensing, so some of those problems go away. I will admit that if you're going to build pivots with this technology on it, you're probably not going to build it this way. You probably then harden things. But at that point, it's a slightly different animal. This is for a research instrument, not for Valley to sell. Though I got a feeling Valley will learn a lot in the process of helping with this. Every tower is going to have GPS, RTK. We will know where every tower is to within a few centimeters. And so we will know where that reader is over that span, over that field at every moment to within a few centimeters. So if you want to go plant one stalk of corn out in the middle of that field and stick your leaf sensor on that thing and come back and visit 10 times a day, you can find it again, and you could do that. And so that sort of precision is not available really in a practical sense today, but it would be practical here. That's a picture of the fiber optic rotary joint. The thing costs about $25,000 as it was quoted to us. That's with electric and fiber. We actually have available one of these. I think Wynn had one for their aerostat balloon, and I believe they've offered it to us to try. It doesn't have the capability I want exactly, but it's a good starting point. There's servers, there's network attached storage, there's all kinds of things that we perhaps would want to do here. There's a functional block diagram of what we propose to build. You know, there is a bottleneck. The bottleneck is sort of coming back to campus. The network bottleneck between Beck and campus is probably too slow to make this thing work well, but that's an upgrade that Purdue needs to do. Well, maybe I can get the NSF to pay for it. I'm fine with that. It's just if you want to do serious research at a research farm only 3 miles away or whatever it is, 4 miles away from campus in a major research institution like Purdue, you ought to be able to connect the networking between these two places as though you were right next door. And you can. It's just a matter of spending a little money, $1 million bucks or something like that. What's $1 million bucks between friends? You know, so I think that's a very doable thing. And I would also argue that you should go clear out to TPAC and to ASREC. They should also be networked the same way. It just makes sense to me. And that's an investment in infrastructure that really should be made so that you can really connect the people working on campus with the people and the experiments that need to run out there. Even if you didn't build a pivot, I would do that. That's what a pivot costs. So the gantry itself is $200,000, and that was putting everything on it. The Valley salesman's like, yeah, you want more? I mean, that's all I got. I can't give you any higher price. You know, now why is that? It's because if you fly over the country from here to California, you're going to fly over many little dots on the ground that you know what they are. They're these pivots. There's thousands of them. This is a well understood technology, and it's an affordable technology for a farmer to buy. And if it's affordable for a farmer to buy, we can certainly gussy it up with lots of interesting sensors and networking and things like that. Use the fact that it's reliable and 50 years of design behind this thing and use it for our purposes. We don't need to make a more expensive platform. We'll put plenty of money into it with the things that we want to research. Anyway, that's what it came down to. I managed to get it under the 500,000 that NIFA would pay for, but then they didn't believe I could. They probably thought with he doesn't, he just ain't going to get it done. It'll cost more. They're probably right. What kind of research would it enable? All kinds of imaging, LiDAR, infrared. You can put climate sensors like Professor Grant has over the canopy anywhere. Instead of reading over a baseline across the whole crop and integrating and solving the problem of why is the measurement, where do I think the measurement is? I mean, the way you would probably do it is some sort of tomography approach. But really what he's doing is just averaging it over the whole canopy. So he's not able to see the, spatial variation in gases that are outgassed from a crop. He's also only able to do it when the weather's nice. This pivot could go over there in the rain. You can do all of these things. You can put a sensor down into the canopy, read the gas density there. You can read it above the canopy. That's a game changer for greenhouse gas study and these sorts of things. You could put radars on it. You could do tomographic root imaging. I'm just pulling everything out of here. You got it all. As a platform, it could allow a lot of things to happen. It could allow a lot of interesting robotics to happen at scale. You could sample thousands of plants a day automatically with this idea. You could put a conveyor along the gantry and bring the pieces, the samples back, gather them there. You don't have to send out. I know it's fun to send the grad students out and keep them busy and see them sweating in that cornfield. There'll still be reasons maybe to do that. Don't worry. But they'll now have thousands of samples in order to do their research. You can look at sort of what is the closing of the loop in an autonomous system here. I've drunk the Kool-Aid so much, I'm a true believer now, and it's kind of nutty. So, hell, I think maybe we'll just put them over everything. And all farmland will have a pivot over it, even if it's got no water, because I can pick the corn automatically from a little robot arm and send it back to the center. That's probably nutty too, but oh, and this is my last, I'm almost, thank God. You could look at cornfields, bean fields, pumpkin patches as systems. You could look at how they operate because you're really able to sense them autonomously and at scale. But even cooler, you could try to prove the concepts of AI and ML at scale in real time. So can ChatGPT grow corn? Well, we have contests for humans already. And the humans are pretty good at it. Humans used to be pretty good at chess too. But there's a human there, old Don Stahl down there, conventional irrigated, 476.9 bushels, 0.9052. Dennis would love that. There's some precision for you. Bushels per acre with a Pioneer brand in Charlotte, Michigan. Center of the corn world. I didn't realize that. But so, this contest, these are interesting because it certainly does show you something about potential of corn. I don't know how much it shows you, and probably agronomists here would have more to say about it, about how it drives maybe practices and things like that. He's growing that where he grows, I believe the contest is such that you have like a 40-acre field that you specify, and then during the season, you're taking care of that field, and you're learning about that field, and you're walking that field, and you're playing Bach for that field, and you're finding out where the corn is the happiest in that field. And then at the end of the year, you pick 10 acres out of that field, I think is what you do. And you get the average computed from that and you win. Well, he's cherry picking, of course, the very best thing that's out there in that whole field. He's applying whatever rate or nutrients or fertilizers, pest control without constraint for the most part on that field to see what can be done. What if we had a different contest though? What if the teams that grew corn were like treatments in an experimental field trial? And we plotted out the land underneath the pivot into plots, and we blocked it if it needs to be blocked and this kinds of things. And what we do is we tell the teams, perhaps you can have a prescription at planting time, something like that, or maybe we just plant a uniform treatment and then let them do other sorts of things, as their management. maybe there's replication, so we have some statistical significance. Instead of saying 476.9052, we know, something about, is that better than 357.4564? I don't know. You need to be able to do experiment design in order to know the answers to those questions. If these teams are the treatments, we can actually give you the significance of which team won, And in that context, ChatGPT could run, because we plant the thing and then we don't allow anybody under the canopy to look at it, to work on it, except through what they see with the pivot. That's all they can do. Their only arms are the robot arms that they designed for the pivot. Their only eyes are the sensor eyes that are running on the pivot. Their only computing is the algorithm that they wrote to raise corn at the beginning of the season, and it's a big contest. And maybe we even measure constraints like the runoff they produce and these kinds of things, and we penalize them for too much, And then we run a contest like DARPA likes to run. We'll call it FARPA or something like that, for Farm Advanced Research Projects Agency. And I've been in this contest, this Spectrum Collaboration Challenge, one of my student groups. Well, we're in it twice. The first time we did fantastic. The second time we did okay. We got to the last, but we did not win. We did not win, and that hurt really bad. The thing I did learn in the process of doing this contest is you don't really want to be in the contest. You want to run the contest. So we want to run the contest. We'll run the contest here at Purdue, and we'll let those people at Illinois come participate. We'll let Iowa State come and participate. See how that goes. But we'll run it. And I suppose if a couple of Purdue teams want to run too, they could. That's my talk. That's all I got. So that's what I want to build.